points quantizations at affine.
So yeah, thanks, and let me start by thanking the organizer for giving me this opportunity to talk here today, and for putting up the conference. It's quite a pleasure to be here and finally be able to discuss with everyone. And so what I would like to present today is some work in collaboration with Kotousov, which is also here at the conference, and Teschner, about integrable sigma models at RG fixed point, and in particular their quantization using what are called affine Gaudin models. So, an introduction, I'll be talking about sigma model, which are two-dimensional field theories whose various application I think I don't need to advertise for this audience. And more precisely, I'll be talking about integrable sigma models, which are the one for which there is infinitely many conserved charges in involution at the classical level. And since the 70s, we have a growing list of examples of such integrable sigma models, for instance, including the integrable deformations we've heard a lot about. And this raised the question of whether there is some common origin, a common theory that describes the integrability of all of these models, or at least most of them. And there's actually several answers to that, which are all related in various ways, including, for instance, what are called 4D Chern-Simons theory, E-models. And here I will take a rather algebraic approach, which goes under the name of affine Gaudin models. And these in particular have been used a lot to explore the panorama of classical integrable sigma models and construct new example of these theories in a systematic way. But today I'd like to talk about another potential application, which goes more in the direction of quantization. So the question is the following: if I have a certain sigma model which is integrable at the classical level, can we prove its integrability at the quantum level from first principles? So really in the sense of I will look at the algebra of observables of this quantum field theory and build an infinite number of charges that commute, and we would like even also to diagonalize it. And this is a famously hard question, but here to make it already a bit simpler, the approach that I will follow is I will start by looking at the integrable structure of the conformal points of these spheres. And the reason for that is that the formalism of two-dimensional CFTs, it actually gives us quite a lot of control and quite a lot of mathematical rigor. For instance, there's less or no UV divergences in this theory. There's the decomposition into left and right moving fields, which in particular quantize to what I call vertex operator algebras, which gives us the right framework to even ask about the question of computing these charges that commute. And so in this context, the main goal of our paper was to explore the applications of affine Gaudin models to the quantization of integrable sigma models at their conformal points. And in the paper and in this talk, I will actually focus mostly on one example, which I'll call the Klimčík model, and which is also called the bi-Yang-Baxter model, which is a specific example of an integrable sigma model. So my plan will be the following. So let me start by saying that although in the end I want to go towards quantization, I think starting directly with the quantum level would be maybe not too pedagogical. So I will actually stay a lot at the classical level to kind of prepare everything we need to in the end go towards quantization. And I will start then by a general reminder about integrable field theories in the Lax formalism. Then I will define affine Gaudin model at the classical level, and then relate them to integrable sigma models using the notion of relativistic realization. And in particular here, I will use this example of the Klimčík model. And then I will look at the conformal limits of this theory in the UV and find and describe in particular its chiral and integrable structures. And this will allow us then in the end to go towards the quantization of these theories. But let me start then with general reminder about integrable field theory through the Lax formalism. So I'll consider a 2D field theory with some fields phi I tx, and I take the space variable x to be in the cycle with periodic boundary conditions for the fields. And the key ingredient for the integrability is the existence of a Lax connection, which is a pair of two matrices L and M that are built from the fields and some auxiliary complex parameter Z, the spectral parameter, such that the equation of motions for the field theory can be recast in the form of a zero curvature equation in terms of L and M. Then if I add this, I consider the monodromy matrix of the spatial component L, the Lax matrix, around my cycle, defined as a parfleted exponential. And a nice result is because of the dynamic of L as the zero curvature equation, the traces of powers of the monodromy in some representation of the group are conserved quantity. And also because we have the dependence on the auxiliary spectral parameter Z, I can expand in powers of Z and get this way an infinite number of such quantities. Now, to really get integrability, we would like the concept quantities to be in involution, so to Poisson commute with respect to the Hamiltonian structure of the model. And so we need to study the Poisson bracket of the Q's, which are built from T and themselves built from L. So in the end, we need to look at the Poisson bracket of L with itself, which will lead to the notion of Maillet bracket. So to describe it, I will use the tensorial notation. So if A is a matrix, then A1 will denote A tensor identity, and similarly here for B2. And then I will decompose my Lax matrix L in a choice of basis of my Lie algebra and look at its components. And now what we can do is, using tensorial notation, I can basically encode all the Poisson bracket between the different entries of the Lax matrix at different values of the spectral parameter and of the space variable into one unique object by contracting them with the basis T A tensor TB. And so this is then an element of G tensor G that encodes all of my Poisson bracket. And just a remark here, because now I'm working with Poisson brackets, so in the Hamiltonian formalism, it means that I'm working with a fixed time. And so now I will remove all the time dependence in my fields. And now the question is there a sufficient condition on this bracket that ensures that the charges extracted from the monodromy of L are in involution? And well, there's several actually conditions that ensures that. Here I will take a rather general one, which was found by Maillet, and which is called a non-neutral local bracket, and which looks as follows here. So there's a term proportional to the Dirac distribution of the space variable, which is what we typically expect in the Poisson bracket of fields in an Hamiltonian field theory. And this term contains then a commutator of the Lax matrix with an object called the R matrix, which is an element of G tensor G, which depends on the two spectral parameters. And then there's also what we call the non-neutral local term, which is the derivative of delta here, which is also controlled by this R matrix. And the result is that if L satisfies this bracket, then the charges extracted from the monodromy are all Poisson commuting, and we really get complete integrability in the Hamiltonian sense. Now, two quick additional remarks on the Lax connection that I will need to use. Well, so far I used the space-time variable T and X, but because I will be looking at a relativistic model, it will be actually quite useful to use light cone coordinate instead, T plus minus X and the corresponding derivative, in which case I can look at the zero curvature equation for the Lax connection in the light code form, which is the one I will use then throughout the talk now. And the last small comment is that the Lax connection in general is not unique. I can always take my connection and conjugate it by some function valued in the group, and I get another connection which then also satisfies the zero curvature equation if the initial one did. So I don't have a unique choice of Lax connection, but then all the charges I extract from traces of the monodromy, they're independent of these choices. Okay, so after this general reminder, I would like to then use this to define a particular class of classical integrable field theory, which are called affine Gaudin models. So to fix the notation here, G will be a simple Lie algebra with a certain basis TA, structure constants describing the commutation relation, and eta will be basically the minus the Bidiner trace in some choice of representation, which is then a non-degenerate invariant Bidiner form on the algebra, which is just proportional to the Killing form. And here I take a minus so that it's positive if the Lie algebra is compact. And because it's non-degenerate, I can invert it, which I denote by raising the indices, and then I will use eta to freely raise and lower indices in my Lie algebra. And in this context, then the classical affine Gaudin model is defined as a certain Hamiltonian field theory, whose fundamental fields are what we call Cox-Moody currents. So precisely here I take n Cox-Moody currents, which are then n fields valued in the Lie algebra, or more precisely the complexified Lie algebra. And in general, I should have reality conditions to ensure that the end results of my theory are real, but I won't enter so much into that here today. The main property that this Cox-Moody current should satisfy is they should have a specific Poisson bracket defining then the Hamiltonian structure of our model, which if I decompose them in components in a basis, then look as follows. So there's the delta term here with some basically commutation relation of my Lie algebra here. And there's a term proportional to delta prime and a certain constant LR, which is a coefficient that we call the level, and which here then will be part of the defining parameters of my affine Gaudin model. And note also that there's a Kronecker delta here in front, which means that if I have the Cox-Moody current with different indices, they simply Poisson commute their independent observables. Now, key ingredient in the definition of the Gaudin model are the so-called Gaudin-Lax matrix and twist function, which are certain functions of the spectral parameter z with poles at n specific point, which we call the punctures zr. And so more precisely, we have as many points as there are Cox-Moody currents, and the corresponding residue at zr in the Gaudin-Lax matrix gamma will be the corresponding then Cox-Moody current, and similarly in the twist function, the residue will be the corresponding level. So now, in particular, inside of my twist function, I have the data of all the parameters defining my affine Gaudin model, the punctures zr and the levels lr. And then inside of my Gaudin-Lax matrix, I have access to all the fundamental fields defining my field. And now what I would like to explain is how from there, we can naturally construct an integrable structure in a sense of Poisson commuting charges built from these Cox-Moody currents. And so for that, I will use the Lax formalism that I just recalled. And in particular, we will define the Lax matrix of the theory as almost being the Gaudin-Lax matrix gamma, which is divided by the twist function phi. So this is a specific function of z, which is a linear combination of the Cox-Moody currents. And because I know the Poisson bracket of the Cox-Moody current, from there I can compute the Poisson bracket of L. And after a small computation, I find that it exactly satisfies the Mayer bracket, as I presented before, with a specific choice of the R matrix, which is given by this expression here. So C here is the split quadratic Casimir, so an element of G tensor G, which is built from the billionaire form. And then there is the twist function appearing here, depending on the second spectral parameter, then keep the information about the levels of my Cox-Moody current. And so now, in particular, the consequence of that is because I have a Lax matrix satisfying a Mayer bracket, then I can look at the monodromy and I can extract an infinite family of charges in involution for the monodromy of L, which in general are non-local charges because they're built as path-ordered from the path-ordered exponential. In addition to these non-local charges, there are also local ones, which were built in this paper, building from some result of Evans, Hassan, McCain, Montaigne. And so they take the following form here. So they're labeled by two type of indices. So one index that just grows with the number of Cox-Moody currents. So if I have n Cox-Moody current, I will have n minus 2 families of local charges labeled by some I. And then for a fixed I have an infinite number of charges labeled by their degree p, which take value in a certain set of positive number e, which is infinite but depend on the Lie algebra that I choose. But it always starts at p equal 2, meaning that I always start with some quadratic charge, and then I can have higher degree 1 cubic quartic depending on the choice of my Lie algebra. And very quickly, the form of the charges is as follows. So they're local in the sense that they're integral over the space variable of a local density, which here is simply built as a polynomial of degree p in my Cox-Moody current components. And these components, they are contracted with some well-chosen invariant tensor on my Lie algebra for the Lie algebra indices. And then the different Cox-Moody currents, they're mixed by some well-chosen choice of coefficients in front of it that depends on the parameters of my Gaudin model, so the punctures and the level. And all these objects should be very well chosen in a very specific way, which ensures that in the end, from the Poisson bracket of the Cox-Moody current, we can show that all these charges, they Poisson commute one way or another. And so we also get an infinite family of local charges in involution from the construction. Now we can actually show that the local charges turns out to Poisson commute with the non-local ones as well. So to summarize the whole construction so far, what we did is we just built a whole infinite family of Poisson commuting charges built from the Cox-Moody current JRX, either in a non-local or in a local way, and which all Poisson commute and which depend on a certain number of parameters, ZR and LR. And this is what I will refer as being the integrable structure of AGMs. It's this infinite number of charges that commute. Yeah.
Can I ask a question? Well, somehow we are taught to believe that all the non-local charge, all what comes from Lax matrix should be complete in some sense. That these non-local charges should cover everything. So those locals can be in principle expressed.
Actually, no. And that we can show, actually, there's an argument, for instance, that the charges that are in the monodromy, in the end, they will have no spin, while here these have
they do have
spin, and so they cannot come from the monodromy. They're just independent construction. Yeah.
Okay.
It's quite different than some other standard field theory, like maybe the KDV, let's say, where the local charges are
it's
extracted
just to
from,
point out whether the direction of superintegrability. You know, you have more charges.
Yeah,
than
we have
the-
more charges than what the Lax connection simply gives us. Yes. Yeah.
But in a sense, the existence at the quantum level of these local charges is actually the important one for quantum integrability, right?
Sorry, could you repeat?
The existence of these ones at the quantum level is what's important for quantum integrability.
Yeah, for
to
instance,
exist.
actually, if we want to apply the argument of Park and so on and the factorization of the ace matrix, that would typically use higher spin. Although I think there are also now some results, I think maybe from Florian Lobert, about how non-local charges can also imply factorization. But indeed, I think the initial argument would be typically using some higher spins ones. Yeah.
And sorry, just to clarify, there's some story that the bottom brackets of the monogamy itself are not well defined.
Yeah, so there's the problem, what is called the problem of non-neutral locality, which is due to the presence of a delta prime in the bi-Yang bracket, which puts some ambiguities in the Poisson bracket of the monogamy itself. So this is actually quite a problem, in particular in the direction of quantization. Let me just say that actually, in order to prove that the invariant of the monogamy, so if you take traces of the monogamy, this then actually you can show in the end without so problem of ambiguity is that this really Poisson commute. It's more to define the Poisson bracket of the entries of the monogamy, maybe like to have some kind of bi-Yang-Baxter equation or something like that, that there is a problem. Another remark here is that the local charges, they don't suffer any of these problems, for instance. Okay, then if there are no more questions, then let me go on. So, well, we just defined this integrable structure of local and non-local charges. Now, just one important property for later of these is that in general they possess a certain gauge symmetry. There will be some kind of local redundancy, which is that if I take the following local transformation of my fundamental fields, of my Kac-Moody current, where H is some arbitrary function valued in the group, so I have the adjoint action on and then some derivative, like in a transformation of a gauge field. Then if I take this transformation, I can look at how the Lax matrix transform. It's a linear combination of the JR, and I find exactly the transformation and the conjugacy of the spatial part of the Lax connection, right? So what we see is that this gauge symmetry here is equivalent to a conjugacy of the Lax matrix by H, which is independent of the spectral parameter. And this has in particular an important consequence, which is that the non-local charges that we extract from L, from the monogamy of L, remember that they're independent on the conjugacy of the Lax connection, meaning in particular that here they're independent of this gauge symmetry, this particular local transformation of the fields. And actually we can show that the local charges are invariant as well, meaning that in the end the whole integrable structure of affine Gaudin model possesses this gauge symmetry. All degrees of freedom are not physical, there is some kind of local redundancy. Okay, so now that I have defined these general affine Gaudin models, what I would like to do is make the link of this with integrable sigma models through the notion of relativistic realizations. So the idea is that so far what I presented is what I would call the abstract or the formal affine Gaudin model, which is really this theory with fundamental fields are the Kac-Moody currents. So the phase space is just the configuration of these currents equipped with the Kac-Moody bracket. Now to consider a realization, what we'll do is we'll take a maybe slightly more standard phase space for an Hamiltonian field theory, which is given by canonical fields in a certain cotangent bundle T star Q, by which I mean something quite simple actually, is I have some coordinate fields phi I x living in some space Q, and then I have the corresponding conjugate momenta pi I, which lives in this then T star part, and they're equipped with the canonical brackets of Hamiltonian field theory, so pi with phi is a Dirac distribution, and a Kronecker delta, and then all the rest is 0. And now to get a realization, I will suppose that there are some well-chosen combination, JRX, of these canonical fields and their derivative, such that the canonical bracket for phi and pi implies that this specific combination satisfies the Kac-Moody bracket. So I realize the Kac-Moody bracket in terms of canonical fields, and because this Kac-Moody bracket is at the basis of the whole construction of the affine Gaudin model, in particular the integrable structure, then I can transfer all this construction to this new phase space, and in particular now I get a bunch of charges in involution, which are now built from the canonical fields in T star Q, because they're built from JR, but JR is itself now a composite field in terms of the canonical fields. Now, let me say that so far, I actually focused only on kinematical aspect, in a sense that I have a certain phase space, so now which is given by these canonical fields in T star Q, and I built an infinite family of charges in involution in there, which I call Z. If now I really want to have a 2D integrable field theory from this construction, the last step that I need to do is I need to choose a dynamic. I need to say what is my time evolution, which I do in the standard way by choosing an Hamiltonian H, whose Poisson bracket will define the time derivative. And I'll take H here to be an involution to Poisson commute with the element of Z, so that by construction the elements of Z are conserved, and they're also in involution, so the theory is then automatically integrable by construction. And a natural choice to have H which Poisson commute with Z is to take H inside of Z itself. And here I'll actually take a very specific choice of that, which is I'll take H to be a linear combination of my quadratic local charges. So remember that I had these n-2 families of local charges which have higher and higher degree, and they always start at quadratic, and here I take my Hamiltonian to be a linear combination of those with some coefficients Si. And that defines then for me that time evolution, and now I really get a 2D field theory with variable T and X. In particular, now that I have T and X, I can ask about the space-time symmetries of this theory. And for instance, about relativistic invariance, so Lorentz invariance under the boost of T and X. And actually, under some technical assumption, we find actually that there is a very simple criteria for this relativistic invariance, which is that the coefficients Si that are defining the Hamiltonian, so the time evolution, should all square to 1. So they should be either +1 or -1. Yeah.
Can you somehow strengthen this result and ask invariance with a special conformal group, for example?
So for conformality, it turns out that classically, these are always conformal.
I see. So, so you can construct not just H, but all Virasoro generator.
Classically, yes.
Yes.
Because classically, we have actually access to all the energy momentum tensor. And for instance, we can show that it's always traceless. And then we ask about symmetric, and that's what gives us the condition for relativistic invariance, for instance.
Okay.
So from there, by looking at the modes of T, we could extract all the Virasoro generators. And so with this simple condition, what I get is that, well, realizing my currents in some canonical fields in T star Q, defining the Hamiltonian, and then imposing this simple condition for relativistic invariance, I get a systematic construction of a relativistic 2D integrable field theory. And with that, I can actually get a whole zoo of integrable field theories just by varying the affine Gaudin model I start with, varying the type of realizations I take, and so on. And in particular, in all of there, I will find a lot of integrable sigma models, which is what I mentioned in the introduction, that this has been used a lot to explore the panorama of these integrable sigma models, and in particular, recover some old ones and find some new ones. And now I would like to show a specific example of this by recovering a specific integrable model, the Klimčík model. And for that, I need to first specify what is the affine Gaudin model I start with. And here I will take a affine Gaudin model with 4 punctures, Z1 up to Z4. And here I choose a specific choice for these punctures in terms of 2 parameters, epsilon1 and epsilon2. So here's the formula. It's maybe a bit complicated, but actually the details do not really matter. I simply take this choice so that in the end it makes some of the equations later quite simpler. And then, so it means that my twist function then will have poles at these ZRs here, and then I choose that the rest of my twist functions simply look like this. And here I have an additional parameter k that goes into there, which is just a global parameter. And now I define my twist function, so I define all the parameters of my affine Gaudin model, the punctures, and the levels which can be extracted as residues of this function phi. So now if I have 4 punctures, it means I have 4 associated Kac-Moody currents, J1 up to J4, and now I want to realize them to get a model. And what I will do here is I will realize them in terms of canonical fields in a cotangent bundle of 2 copies of the Lie group. So here the idea is that if I have canonical fields in T star G, there is an explicit formula to build from there a pair of Kac-Moody currents. The formula is really explicit, but I won't give it because it would require introducing a few notations. But now I just take 2 independent copies of this construction, which is now then in 2 copies then of T star G. And I get then 4 Kac-Moody current from there. And by construction, then my realization of my Gaudin model will be then an Hamiltonian field theory in T star of G cross T, which means that if I go to the Lagrangian formulation, I will eliminate the canonical momenta, so basically I will get rid of T star here, and I will get a Lagrangian model on G cross G, which is then described by two fields valued in the group, which I will call here G1Tx and G2Tx. And I remember also that there was this gauge symmetry in the affine Gaudin model, so there was some kind of local redundancy. And for this choice of realization, one can prove that it acts on the fields G1 and G2 simply by right diagonal multiplication. So in the end, the real physical model that I get is an integrable model on G cross G, quotiented by the diagonal action of G, which I can identify simply as G itself. And one way of doing this identification is I take G1, G2 inverse, which of course then is because of this transformation, this is gauge invariant. So these are real physical degrees of freedom of my model. And now I will skip all the details, but if you do all this construction, you take the Hamiltonian, you plug it in the formula of the, coming from Gaudin, you do the inverse Legendre transform to go to the Lagrangian, express everything in terms of the gauge invariant field, you end up with this thing here. So before I talk about the interpretation and what identify this model, let me explain what are the ingredients in there. So we see that we have actually a sigma model form with the current G inverse D plus G and G inverse D minus G, which are contracted through the trace, so through our Billiner form on the Lie algebra. And in the middle, we insert some inverted operator, which is built from two types of objects. So I have my parameters epsilon 1 and epsilon 2. And actually, the reason I took this rather complicated expressions for the punctures was to make, in the end, the action as simple as possible. And then in front of these, I have some operators, R and Rg. So R is simply the Drinfeld-Jimbo R matrix. So it's a linear operator on the complexified Lie algebra, which we also saw, for instance, yesterday in the talk of Fiona, for instance, which act as 0 on the Cartan subalgebra and as plus minus on the nilpotent generators. And then Rg is simply R decorated by some adjoint action of the group valued field. And now some of you might recognize actually this sigma model. It turns out to be a sigma model which was quite well known before, and which is the Klimčík or bi-Yang-Baxter model, which was introduced by Klimčík in 2008, and which was introduced as a particular two-parameter deformation of the principal chiral model that correspond to the case epsilon 1, epsilon 2 equals 0, where we have just G inverse dg, G inverse dg, which is a famous integrable sigma model on the group. And well, this particular model, it was proven also that it was integrable, that, for instance, there exists a lax connection. And from our point of view here, because we recovered it from an affine Gaudin model, then it should also be integrable automatically. And for instance, there should be a lax connection that comes from the affine Gaudin model construction. And if we do the computation of what it is, we find that it's the same as the one found by Klimčík, actually equivalent, gauge equivalent to the one that was found. And in addition to the lax connection, we also have the local charges. So these, I think, were not known explicitly before for this bi-Yang-Baxter model, but they turn out to be deformation of some charges that were found by Evans, Hassan, McCain, Montaigne for the case of the PCM. So to summarize, what we see is that the Klimčík model is then a certain relativistic realization of a specific affine Gaudin model with 4 punctures. I make a very specific choice of punctures, a specific choice of realization. I turn on the machinery, and in the end I get this model, and I recover some of the known features of this model that were found before. Yes?
As you showed, of course, there's the affine quantum group symmetries that come from the non-local charges. Is there an algebraic understanding of what this deformation is on the higher spin charges?
How the...
yeah, what this deformation of... Is there a charge algebra of these
so I think
local higher spin charges?
The local higher spin charges, they will be invariant, I think, under these affine Q-deform symmetry in general. So actually, I think the affine symmetry, it was found only with a case where there is only one deformation, probably explicitly done. Probably it should be the case that there is 2 of them here, but so far I'm not sure it has been proven. But I would expect that the local charges are just simply commuting with all the generators of this. Okay, so, well, so far you might have remarked that I have no nothing about conformal limits, which was part of my, about the RG fixed point, which was part of my title. And so now in the second half of this talk, I would like to then describe the conformal limit of this model, more precisely the UV limit, and describe its chiral and integrable structures. So far I've seen the Klimčík model as a classical field theory with 3 parameters, k epsilon 1, epsilon 2. Now if we look at this quantization, we'll encounter UV divergences as usual, which we need to treat by adding counter terms, which effectively tells us that our parameters will become dependent on the energy scale mu of the renormalization group. And this dependence can be described by the one-loop RG flow, which was found in this paper. So there are some proportionality coefficients here, which I don't put because they're not so important. This is one loop, so it's order 1 in H bar, and they should be then in general higher order correction, of course. And what's mostly important for us is that it's proportional to this coefficient xi squared, which is just a specific combination of my deformation parameters. Now let me just make an observation, which is, well, we've seen already the bi-Yang-Baxter model yesterday in Dan's talk, but actually here I'm using a slightly different reality condition regime for the parameters, which changes a few things here, in particular a few signs. And in particular, this has an important consequence, is that this will have a well-defined UV limit. And if we do the UV limit, so we just follow this flow to mu equal infinity, to the high energy, what we find is that it sends epsilon 1 plus epsilon 2 to 1, which is consistent because we see that it sends then this parameter xi to 0. So we get that the right-hand side of the RG flow is 0, so we have 0 beta function, which is what we expect because in the UV we want a conformal model where the couplings do not run. And in the following, I will actually parameterize this UV limit in the following way in terms of KUV and nu. So nu is just a parameterization of epsilons such that in the end the sum is equal to 1. And then KUV is just K rescaled in a specific way. And once again, this is to make some of the expressions later simpler. The details are not so important. Now, this was maybe a little bit abstract. So to give an example, a concrete example, we can look at maybe one of the simplest case of the Klimčík model, which is when the group is equal to SU2. And in this case, it turns out that it's actually equivalent to another model that was found by Fatih, and I think the relation was proven in this paper, which is a certain squashed free sphere, squashed in 2 different ways. And to describe it explicitly, we can introduce some coordinate fields, 3 of them, because SU2 is 3-dimensional. And here I'll do this by using a modified Euler parameterization. So I take my group valued field G, and I write it in terms of 3 fields, phi, alpha, and chi, in the following way. So once again, the details are not so important, but the 2 angles here, I actually do a specific linear combination. And then the angle in the middle, I take it to be an arctangent of exponential phi. Well, then I put this back into my action. I compute everything. I take the UV limit. And in the end, we find something which is quite simple, which takes the following form here. So we see that, for instance, the boson chi here, it actually, in the UV decouple, it completely decouples. And it just becomes a free boson on its own. And then the 2 other fields, phi and alpha, they stay interacting, but they take a rather simple form here, which some of you might recognize as the cigar sigma model, which is a certain specific 2D sigma model in terms of these 2 fields. And in particular, the cigar sigma model is well known to be a conformal model, which is here consistent because in the end we want a conformal. I mean, the theory should be conformal because we took the UV limit, and here it's conformal because it's the cigar plus just a free boson. And I must say, I mean, this is actually only locally. There are some globality issues, but I won't talk about this today. Now, what I mainly would like to talk about is what happened to the integrable structure when we take this UV limit. So we had all this construction of charges that commutes before the UV limit, and I'd like to see what happens, and in particular what happens to the Lax connection when we take the conformal limit. And so if we do the computation of the Lax connection before the limit, we find that it has actually a very simple dependence in a spectral parameter. So the L plus component depends only on Z, and the L minus only in 1 over Z. And then we see that the part that contains the spectral parameter dependence always come proportional to the coefficient xi, which was this specific combination here of the deformation parameter. And then here, B and I, they're just some specific currents which are built from the field G, whose expression I don't really need. What's important is the presence of the xi here, because recall that in the UV limit, xi is sent to 0. So if I take the limit too naively, I completely get rid of the spectral parameter dependence, meaning that my Lax connection becomes somehow trivial. I can't extract an infinite number of charges from there. So I will need to take the limit in a slightly more subtle way. And for that, I will change my spectral parameter. I will introduce a new one called ZL, and I will explain why L later, which is just xi times Z, and this I now keep fixed. And if I do that, I see that in the L plus component, well, I have xi times Z, so I keep a non-trivial parameter dependence in ZL. But then in L minus, then this becomes xi squared, and then I just have the UV limit of my constant term only. Now I can do something slightly symmetric, which is I consider what I'll call ZR, which is now xi over Z. And in this case, I keep the non-trivial dependence in the minus component, and in the plus component, I get rid of ZR. Now to understand the consequence of this limit, let me focus first on this case ZL, and I'll come back to this one a bit later. So the main property of this limit is that the minus component becomes independent of the spectral parameter. And this means that I can eliminate it very simply by a gauge transformation. So recall that I had this gauge symmetry that acts on the Lax connection just by conjugacy of the connection. So in particular, if I take the parameter to be the path-ordered exponential of this B minus, then I can get rid of this particular dependence in L minus, which means that in the end, I should have a Lax connection, which in a specific choice of gauge, look as follows. The minus component is actually 0, and then I kept a non-trivial dependence on the spectral parameter in a plus component. And this has an important consequence when I look at the zero curvature equation. So recall that L plus and L minus originally satisfy a zero curvature equation, and this is kept in all of my procedure here, because if I change the spectral parameter, take the UV limit, or change the gauge, I keep the zero curvature equation. And if I look at the zero curvature equation in this gauge, well, because L minus is 0, this simply becomes D minus L plus equals 0. So that tells me that L plus then is a chiral field. More precisely, it's a left-moving field, right? It depends only on T plus X, so it's moved only to the left. And this actually is something that is maybe natural to see appearing in a CFT, because we know that in a CFT we have decoupling of the left-moving and right-moving chiralities. And what we see is this actually happens also at the level of the Lax connection, where our Lax connection now becomes dependent only on, let's say here, left-moving fields. And let me observe that in general, so these fields BL and IL, which are then the left-moving objects, in general there will be non-local fields, and the reason is that we had to do this gauge transformation by a path-ordered exponent at some point, which then introduced some non-locality in the procedure. So in general, this can be rather complicated field, but they're left-moving, which is nice. Now, of course, I could do the other thing with now the ZR spectral parameter, in which case I get in the end to L plus equals 0, and I keep the minus component, which of course will be then expressed in terms of right-moving field. And this is why I have these notations L and R, therefore left-moving and right-moving. And so to summarize, what we see is that at the UV limit, our integrable structure that initially was defined in terms of just one unique Lax matrix, it will actually decouple. It's split into two decoupled integrable structure, one in terms of left-moving chiral half and one in terms of the right-moving chiral half. And this is, well, indeed something that really is quite relevant in the context of a 2D CFT. Now, so all this was maybe once again a bit abstract, so let me give an example of this whole procedure in the simplest case of G equals SU2. So recall that in this case we had just a free boson chi plus a cigar sigma model. And if we do this whole thing of computing the limit of the connection, going to the gauge where it's chiral, we find the following result in the end. So in the diagonal, I have so these are the parameters, this is the spectral parameter, and in terms of the field, I guess I get D plus chi. And because chi is a free field, then of course D plus chi is left moving consistently as with what we expect. Now what's less trivial is what's happened in the off diagonal, which is related to the cigar sigma model, which is in particular a non-trivial interacting theory. And what we find in the end in the Lax connection is the so-called parafermionic fields of the cigar, which are defined as follows. So they're a bit complicated. For instance, they involve some square root of the field, and also the non-local, because there is this dual field here that appear, which is defined as a certain integral. And this in the end comes from this gauge transformation. And well, the details do not really matter. The main property of this is that if you derive the equation of motion of this cigar sigma model, you can check that these are really left moving. They're killed by D minus. And so in the end, these are the fields that I get in my lacks connection for this specific case. Now, in particular, recall that in all that I've studied, I want to look at Hamiltonian property, in particular Poisson bracket of everything. And well, here one can wonder also what happens to the Poisson bracket of the theory in this conformal limit. And in particular, there is a nice property that, so we saw this decomposition in left moving and right moving, and there is a nice property that the Poisson bracket of a left moving with a left moving field will also be a left moving field. So they close in the Poisson bracket, and they form what we call the chiral Poisson algebra. So here we can look at what it looks like for this specific example. So the free boson we know is left moving part plus right moving part. And it's standard that the left moving part then satisfy the following Poisson bracket, where epsilon is the sign function, so -1 and then +1. And in particular, this is a non-local bracket. It's not given only by Dirac distribution. There is this non-locality in the epsilon. If I look at my parafermions, they're actually quite complicating object, but it turns out that they satisfy a quite simple Poisson bracket, which is closed, and which take the following form here, which is then on the right-hand side quadratic in my parafermion, also with some non-local epsilon term, and there's a delta prime that is staying here as well. And this is just a consequence of this definition. And of course, I have similar Poisson brackets for the right moving fields. It's just more or less the same with some signs that change here and there. And then the left moving and the right moving, they all commute one with another. And this defines then my two chiral Poisson algebra of left moving and right moving, in which then I can work to guide integrability. So far I had these parafermions, which were rather complicated non-local fields. And I can wonder maybe, are there also some local chiral fields? And in fact, you can find some by looking at very specific combinations of the parafermions. So the parafermions, they're non-local because there is this dual field here. So in particular, if I take, for instance, psi plus times psi minus, I cancel the exponential, and I get a local object, which is actually quite simple written in terms of the field. And we can check that this is indeed a chiral object. It's a left-moving object. And then I can construct other ones also by looking at derivatives of the parafermions. And for instance, this specific combination turns out to be local. And I can actually build it for every spin. So here this was spin 2, spin 3, and then at spin 4, spin 5, and so on, I will find a new field a new independent field each time. And all of these then form a bunch of left-moving local fields, which actually also are closed in the Poisson bracket. So they also form a subalgebra of my non-local chiral algebra of parafermions, which is what we call the W algebra of the model. So the algebra of extended conformal symmetry, which contains all these local left-moving fields. A typical example of an element in this W algebra, which is always there in a 2D CFT, is the spin plus 2 component of the energy momentum tensor. So the energy momentum tensor of a 2D CFT will have a left-moving spin plus 2 part and a right-moving spin minus 2 part. And in the present case, the spin 2 part, it looks as follow here. In particular, it satisfies also a closed Poisson algebra in itself, which is nothing but the classical Virasoro algebra. And then I can have other type of W currents, also of higher spins, and they all form closed Poisson bracket, which are quite more complicated in general than that, but which are always local in the sense that there's no epsilon. It's only some delta and derivatives of delta. And now a remark is that if I take any field W in my W algebra, because it's chiral, of course, its integral defines a conserved charge almost trivially. So I get a lot of conserved charges, but now because I'm interested in integrability, I would like to ask about involution of these charges. And I find that in general, all of these, they do not Poisson commute one with another. But I can actually find inside of there a subset that commutes by looking at the local charges I had in the Klimčík model initially from the affine Gaudin model construction and taking the limit. And these turns out to be actually quite simple. The density is simply powers of the energy momentum tensor in the present case. And this you can check from the Virasoro algebra that they all Poisson commute one with another. And so this is quite simple, but let me say that actually this is only a classical result. When we quantize these local charges, they turn out to not be expressed only in terms of the energy momentum tensor. You also need to add other higher spin fields, non-trivial higher spin fields of W algebra. And finally, let me observe that, of course, all this was for left moving, but there is a similar construction for right moving where there is a W algebra, and I can find some charges in involution in there. So to summarize what I have so far, well, the main idea is that we look at the integrable structure of the Klimčík model at the CFT point, And what we found is that classically, we get a lot of non-local and local conserved charges in evolution, which quite importantly are now built either in the left-moving or in the right-moving chiral-Poisson algebra. And the conservation is actually somehow trivial. It's always just a consequence of the chirality. And well, once I have identified my chiral fields, then of course I kind of trivialize the dynamic. So the conservation property here is not so difficult. But what's important is that it's the involution of the charges, which is, okay, thanks, which is non-trivial. And which is then just, here it's a non-trivial question. I have a certain chiral algebra with certain Poisson brackets. And inside of there, I want to build charges that commute. So now what I would like to say is just comment on what happened from the point of view of affine Gaudin model in this limit. So recall that the initial Klimčík model was a relativistic affine Gaudin model with 4 punctures. And now when I take the UV limit, what I've learned before is I need to take this with different spectral parameters associated to left and right moving. And what happens if I do this is I see that I will have some collision of some of the poles and the zeros of my twist function. And the poles, remember, are the punctures, which mean that in the limits, I get basically less punctures in the end. And so I get 2 different twist functions, phi L and phi R, which have each 3 punctures. And so the interpretation is that this thing of the separation of the 2 chirality happen also at the level of the AGM. Initially, I have one affine Gaudin model with 4 punctures that describe the whole model. But in the UV limit, I need 2 different affine Gaudin model, but which have less punctures, so which are associated to less degrees of freedom. And one will describe left-moving, and the other will describe right-moving fields. And that leads us in particular to the definition of what we'll call a left-moving, a chiral realization. So here left-moving, but they could be right-moving. So it's still a realization in the sense that my Klimčík current are expressed in terms of canonical fields in T star Q. But now we ask in addition that the dynamic is such that the theory decouples into 2 chiral halves of left and right moving. And we ask that our Klimčík current JR, they're here expressed only in terms of, let's say, left moving fields. So they're in a left chiral Poisson algebra.
Maybe I missed this point. So in SU2 cases, you mentioned in the conformal limit, you just get SL2R coset model times the line.
Yes.
Can one make some more general case comment about what is interpretation of other general case?
So for instance, for higher rank group, we don't have a proof. But what we kind of expect, looking at some cases, is that it will become just rank G free boson plus the CFT point of the coset G over H, where H is the Cartan subgroup. And this, at least in terms of we computed some Poisson algebra of like parafermionic-like Poisson algebra in the gauge fixing of this higher rank model, and we find something which is consistent with having basically the parafermion of G over H, and then rank G free boson. Okay. So here in this definition, so in this left-moving chiralization, so the Klimčík current should all be left-moving. And actually, to be more precise, they should be left-moving in a specific gauge. And so this is because, remember that to get to really the case where the lax connection in the end is left-moving, we needed to do a gauge transformation. So here, the Klimčík current in a specific gauge fixing, they should be left-moving. And then all the things that I presented before, they can be reinterpreted in terms of affine Gaudin model. So in particular, these gauge fixed currents where they become left-moving, they will become my non-local chiral field. So this is how I will get, for instance, the parafermions from the affine Gaudin model. And then the local chiral fields, so the W algebra, they correspond to gauge invariant differential polynomials in my Klimčík current, and they form what is called a coset W algebra in the standard terminology. So now what I want to do just in the few minutes that I have left is just to say a few words about the quantization of this. And so the idea is that now that we have this integrable structure in chiral Poisson algebra, we have a rigorous and well-controlled setup to go to the quantum level because we know how we quantize chiral Poisson algebra. These quantize in what are called vertex operator algebras, which then describe the quantum chiral fields and their commutation relation. And now with this picture, I now have a well-defined framework to ask about the construction and diagonalization of commuting charges in these VOAs, which can be either local or non-local in the quantum chiral fields. And this is then a hard but well-defined mathematical question, which is really what here, for instance, the CFT brings us. And for instance, if I look at AGM, if I look at quantized AGM, this will be described by a certain, what we call the affine Klimčík VOA, or actually n copies of this affine Klimčík VOA, which describe my quantum Klimčík current JRX. And the Poisson bracket that I had for the classical currents, now at the quantum level, they become commutation relation, which are encoded in the language of VOA in operator product expansions. And the OPEs of this Kac-Moody current, it looks as follows. So there's a simple order pole here, which is the delta term in the Poisson bracket. And there's the second order pole, which is the central extension, so the delta prime term, proportional to the now quantum level KR. In particular, now that I have this OPE, which encode my quantum commutation relation, I can ask about the integrable structure. I can ask about building some specific combination of these quantum JRX, either local or non-local, which would be then commuting. And then also I would like to find the spectrum and diagonalize them on some representation. So here it's not fully understood yet, but there's a lot of first results and conjectures that shows that this integrable structure at the quantum level should exist. And in particular, we can look at what happened for this specific case of the SU to Klimčík model in the UV that I had. And here there's two main approaches. Either I look at things coming from affine Gaudin model point of view. In particular, I have a rather simple description of the quantum coset W algebra as a certain specific coset. And inside of there, I can ask about the quantization of the local charges. So these quadratic and so on charges, we can quantize at least the first ones using some results here. And then another approach is based on what are called screening charges in free field realization. So I won't have time to explain about this, but just to say that in the end, this gives us some conjectures and results about also the quantization of the local and non-local charges in this model. And what we checked in our paper is we look at the agreement of the first local charges. So the first local charge is the spin 2 density. This is actually rather simple to quantize. It just becomes the quantum energy momentum tensor, the density. But then the first non-trivial one is a quartic one, so a spin 4 density. And here we computed it from the affine Gaudin model point of view and from the screening charges, and we find that it exactly then coincide, which is already a non-trivial result in this case. So this then was mostly what I wanted to say. Let me just briefly conclude. So what I presented about this first step then towards quantization of integrable sigma model using AGMs at the CFT point. One of the interests of AGM is that it brings a lot of hope for natural generalization and perspective. So for instance, going higher rank for the Klimčík model, and here, well, we have some first initial results in the paper, that there are still a lot to explore. And mostly is the idea that we can apply these to a quite larger class of relativistic AGM. So recall that the Klimčík model corresponded to 4 punctures. So I can look at more punctures of a type of punctures, for instance, of higher order poles and so on. I can change the realization and, for instance, go to lambda model rather than Yang-Baxter deformation. And all of these ideas, looking at the CFT limit, should also apply to all this zoo of here. And then also we can ask about what how all this can be interpreted in other formalism, like the E-models or the Fordich and Simons formalism, which we know are related also to the AGM construction. Then, so far I focused only on constructing the quantum charges that commutes, but then we can ask about diagonalizing them and describing the spectrum. And here let me say that there is a very powerful approach which is called the ODE IQFT correspondence, and which was actually one of the main motivation behind the introduction and the study of affine Gaudin model and also of our paper. And well, I won't have time to describe, but here we also made some check that there is some agreement of what come from affine Gaudin model and what come from other approaches in this paper here. And finally, let me say that probably the most important but the most difficult question is to go beyond the CFT, so to try to go to points which are not fixed under the RG. And here this is of course quite a complicated question, but maybe one can hope that the CFT can serve as an entry point, and we can start with the CFT point and then try to build from there the massive case by putting back together the left and right moving chiral halves, and hopefully at some point get some result about the integrable quantum structure from first principle. And with that, I end and thank you for your attention.
Questions?
I think that was
Yes, if we add the West-Suminovitan term, like yesterday Fiona did, this is still covered by this affine Gaudin model?
Yeah, so so we didn't really look at the conformal limit, but I think so. It's some unpublished result, but this case is also an affine Gaudin model. The only difference is it changes a bit the levels.
But it remains 4 rank.
Yeah, it's
four punctures.
Yes, exactly. It's still 4 punctures, but then it changes a little bit the levels that enters in the affine Gaudin model. In particular, one of the effects is here, because there was no Vesuvian term, there was some kind of parity symmetry between left and right moving. And actually, the left and right moving affine Gaudin model, they had the same level up to a minus sign. And this actually will be broken if we add the Vesuvian term. Actually, the Vesuvian level, we just add to this level directly, and then the left and right moving will be slightly different algebraic objects, basically. But it should be covered, I think, from this construction. Yeah, done.
I mean, the ones yesterday were multi-parameter conformal deformations. Right? There was a marginal manifold of theory. So if you start with like a super coset version of this, do you hit the VOA on the head from the outset?
That maybe not. I mean, one of the things is here, we really had to take this very specific limit in which it becomes conformal. I guess if you have a supergroup, and if you start with a supergroup which have like vanishing Coxeton number, then you will always have then conformal invariance. But I'm not so sure how easily it is then to identify the left and right moving sectors, and whether we can do a whole this construction as simply as that. So that for the super case, I think in some sense the origin from conformal invariance is maybe a bit different. It's I mean, of course there should be some relation, but it's really because in the end there is this A check that cancel, which is slightly different mechanism than what happens here.
So this is a bit related to Akari's question earlier, but so you started from SU2 and then you end up with SL2R over U1, and I guess the question is, so do you need to glue together formally different cigars to?
Yeah, so this is part of what I meant when I said that here in the limit there was this locally. So there's two things actually behind this, which are to do about the target, how the target space looks like in the limit. So first of all, actually, this thing of free boson plus cigar, it's not exactly true, because the free boson chi, it's not really on the cycle, because if I look at the basically the identification, when chi goes to chi plus 2 pi, I actually need to change also the value of alpha, so I kind of glue it non-trivially on there. So here there's also, it's not completely separated, the cigar and the field. And then also there is this thing that there is all the charts. So it's a bit like the sausage, that in the end on one chart will become the cigar, on the other side will become the right cigar, and in the middle there will be some asymptotic domain, which is just the cylinder. Here there will be something quite similar. There is, on one, I can get the left cigar here, I can get another cigar with another way of taking the limit. And then in the middle, I have basically some free field, which is where I get these screening charges and the free field realization. And actually, these two, what's also important is that it's not phi and alpha that are the coordinate of the other cigar. It's actually so phi stay the same, but then instead of alpha, I have alpha twiddle, which is a non-trivial mix of alpha and chi. So the gluing is rather non-trivial here, which actually I think is one of the reasons why we can't really say that this is just the cigar integrable CFT plus the free boson. There's some non-trivial thing that actually are kept track here in when we glue things together in a non-trivial way.
Okay, thank you. And just another question. So I guess SU2 is very special in the sense that the model you end up with is real.
Yeah.
Just out of interest, the whole conserved charge stuff, does that go through for when it is?
Yeah, so you ask about the art questions. So indeed here we had to take this analytical continuation to get a non-trivial UV fixed point, and we were safe because in the UV, for the SU2 case, and so in general what we would get is we get a real metric but a imaginary B field. And in the case of SU2, the B field turns out to be total derivative, so we can get rid of it. For higher rank, in general, we should probably keep some non-trivial B field. But in some sense, it's not such a problem for all the algebraic manipulations we do. I mean, maybe there will be some issues with, for instance, unitarity of the CFT that we're going to consider. But if we just ask about commutation relation and building stuff that commute, that should probably go through. Another point on that is maybe also we can look at case with non-compact group initially, and in this case we should have we can take the split R matrix directly, and then it should work. But then we lose the boundedness below of the Hamiltonian probably.
Thanks for the nice talk. So the first question is really about the Maya bracket. So when you take this limit and you go to the UV, so there are some models like the K-deform PCM where you take a limit and you completely ultra-localize the model. But here when you take the limit, it seems that the twist function is not a constant. But could there be like some gauge transformation where the Maya bracket ends up being ultra-local?
No. So there is an example. So it turns out that, for instance, the cigar, if you take the sausage grid to the cigar on its own, then here there's a gauge where it will become non-ultralocal, ultralocal. But actually, in the case that we're looking at here for this full Klimčík model, there's no gauge where it's ultralocal, except if you put the parameter nu to 0, which effectively goes back to the cigar, actually.
I see.
So here we really can't get rid of non-ultralocality.
I see. And one more question is, you have W algebras appearing in your setup and also affine Catch-Moody algebras. So you can get W algebras from affine Catch-Moody algebras from generalized Siegel-Sugawara constructions. So are these related in that sense, or are these like completely different
Yeah,
objects?
so I mean, here it turns out that, for instance, the W algebra that naturally comes from affine Gaudin model is built as a coset W algebra. So I take just 2 copies of the Catch-Moody current and I quotient by the gauge symmetry, basically, which is, and then, for instance, the 2D, the energy momentum tensor in there is built by the Siegel-Sugawara there, the Siegel-Sugawara there, minus the diagonal Siegel-Sugawara, which are this kind of JKO construction, for instance.
Thank you.
Yeah, it's on. So 2 questions. The factorization that happens, do you expect that to just be in the CFT limit? Do you expect that to be generic?
Yes, so this, at least at the classical level, we looked at this very general class of relativistic AGM with more punctures, arbitrary punctures, and so on. And we have some kind of general argument that there should be a limit in which we have this property that we have 2 lax connection, and one will have 0 minus component and the other 0 plus component. So there should always be chiral fields that we should extract from there.
Okay. Have you any idea about how you might specify the affine Gaudin model data in terms of the CFT data? Like we can factorize CFTs, right? We understand really well how to do that. So maybe you can see what the CFT data is in terms of the affine Gaudin model.
Yes, so I think partly. So, for instance, the central charges can be very easily obtained because, for instance, we have the W algebra as a coset construction, so we can apply the general formula for the central charge. Another thing is, well, if we ask about what is the quantum VOA, then actually it should always be something built as, well, having a bunch of Catch-Moody current and building and then gauging this. So for the local charge, we, I think, understand that pretty well, and it gives us the for the local densities, it gives us the W algebra. Then, for instance, there should be a way to take quantum Catch-Moody current, do some BRST reduction, and we get, for instance, the parafermions and all that. So in general, we should have access to the algebra, even of non-local chiral observables from there, although in practice it can probably be quite difficult.
Okay. And do you have any idea about what happens to this factorization as you move away from the CFT limit?
So probably then it will be broken, right?
Yeah. I mean, it might be like if it's still integrable, you'd expect it to be that you at least you'd hope that there might still be some nice structure going on. So
probably what should happen is we should recombine the left and right moving hulls in a very specific way. That is, we do a marginally relevant perturbation from this point. That it will be probably like quadratic in left and right moving stuff, chosen in a very specific way that ensures the integrability of the theory. But doing that at the quantum level, I think, for the moment is quite hard, right?
I think we're running short on time, so maybe let's thank Sylvain again.